Let us solve a problem on single line to ground fault condition. A salient pole generator without dampers is rated at 25 MVA, 13.2 kV and has a direct axis subtransient reactance of 0.25 per unit. The negative and zero sequence reactances are 0.35 and 0.1 per unit respectively. The neutral of the generator is solidly grounded. Determine the subtransient current in the generator and the line-to-line voltages for subtransient condition when a single line to ground fault occurs on the terminals of an unloaded generator. So, a generator is given, its ratings are also given, its positive, negative and zero sequence impedances are given, and we have been asked to calculate the subtransient currents in the generator. That is, we have to calculate the phase currents IA, IB and IC under fault condition, then and the line to line voltages when a single line to ground fault occurs on the terminals of the alternator. So we know how to calculate the fault current. So let us start from that. So the direct axis subtransient reactance, that means the positive sequence reactance. So Z1 is equal to given Z1 is equal to 0.25 per unit. Z2 negative and zero sequence reactances are Z2 is equal to 0.35 per unit and Z0 is equal to 0.1 per unit. Now we know the equation for calculating the fault current. And one more point. So there is no information regarding the neutral grounding impedance. So this is total Z0. Total value of zero sequence reactance will be 0.1 per unit. And also no information is given regarding the fault impedance. So we can assume this as a direct short circuit fault. So ZF is equal to 0. So Zn is equal to ZF is equal to 0. Now let us calculate the fault current. We know the equation for calculating the fault current. IF is equal to 3 times EA divided by Z1 plus Z2 plus Z0. Okay. So 3 into EA. The generated EMF of the generator alternator can be taken as 1 angle 0. So 1 angle 0 per unit divided by Z1. Z1 is J 0.25 plus Z2 is J 0.35 and Z0 is J 0.1. So while solving the unsymmetrical fault analysis problems, represent all the parameters as complex quantities. So that is why we are using J 0.25, J 0.35 like that. So solve this equation and we will get the value of the fault current as minus J 4.2857 per unit. Minus J 4.2857 per unit. So this is the per unit value of fault current. So if we have to calculate the actual value of fault current, we need to know the base current. So let us calculate the base current. So base current IB is equal to MVA base into 10 raised to 3 divided by root 3 into kV base. So here MVA is 25 and kV is 13.2. So 25 into 10 raised to 3 divided by root 3 into 13.2, and we will get the value of current as the base current as 1093.466 ampere. 1093.466 ampere. So we got the base current. Now per unit value of fault current IF in per unit equal to actual value in per unit, there's a mistake. Actual value of fault current IF actual will be equal to per unit value into base value, that is minus j 4.2857, which is the per unit value, into base current, that is 1093.466 ampere. So let us take the magnitude of this quantity only. So when we express this in polar form, it will be 4.2857 angle minus 90. So I am taking the magnitude only. So 4.2857 into 1093.466 will be equal to 4680. So we will get the actual value of fault current as 4686.28 ampere. So we have to calculate the subtransient current in the generator. That means the current through all the phases under fault condition. So we have to calculate IA, IB and IC. So see, let us calculate subtransient currents in the generator. Subtransient currents in the generator. So if we have to calculate IA, the current through phase A, IA, is equal to IA0 plus IA1 plus IA2. So if we have to calculate IA, we need to know IA0. IA0 only, because for a single line to ground fault, IA0 equal to IA1 equal to IA2. So we need to calculate IA0 only. So how will we get the value of IA0? So we know that in case of a single line to ground fault, the fault current IF is equal to 3 times IA0. Okay. Therefore, IA0 is equal to the fault current divided by 3. IF divided by 3. IA0 will be equal to IF divided by 3, which will be equal to IF is minus j 4.2857 divided by 3, and the answer will be equal to IA0 is equal to minus 1.4286 minus j 1.4286 per unit. So we have IA0. The phase current IA will be equal to IA0 plus IA1 plus IA2, or 3 times IA0, which is again same as IF. IF and IA are the same. So we can write IA is equal to IF. So we got the value of subtransient current in phase A. That is IA is equal to IF is equal to minus j 4.2857 per unit. Okay. So next is the current through the remaining two phases, phase B and phase C. So if we are assuming that the fault is occurring on phase A, current through phase A will be equal to fault current. So we have done it, and in the question it is given that the alternator is unloaded. When a single line to ground fault occurs on the terminals of an unloaded alternator. So unloaded means current will not flow through the phases other than the faulty phase. Through the faulty phase, a current will flow towards the ground, and as the alternator is unloaded, no current will flow through the remaining two phases. So subtransient current in phase B will be 0. Similarly, subtransient current in phase C will be 0. So we have calculated all the currents. Now we have to calculate the line to line voltages. So if we are considering a 3-phase alternator and ABC are the phases, the line to line voltages are VAB, VBC and VCA. VAB, VBC and VCA. And we know how to calculate VAB. So VAB can be written as VA minus VB. Similarly, VBC is VB minus VC and VCA is VC minus VA. So in order to calculate the line voltages, we need the value of phase voltages VA, VB and VC. So the phase voltage VA can be expressed in terms of symmetrical components as VA0 plus VA1 plus VA2. VA0 is equal to, VA is equal to VA0 plus VA1 plus VA2. So for that, first of all calculate VA0, VA1 and VA2. VA0, terminal voltage of zero sequence network. VA0 is equal to minus IA0 into Z0, which is equal to, we have got the value of IA0 as minus J 1.4286, minus J 1.4286. So IA0 into, IA0 is minus J 1.4286. So minus of this term into Z0. Z0 is given as J 0.1. So answer will be minus 0.1429 per unit. Minus 0.1429 per unit. So here J into J square, which is minus 1, minus into minus plus, and again this minus will be here. So VA0 is minus 0.1429 per unit. Next is the positive sequence voltage VA1, which is equal to EA minus IA1 Z1, which is equal to EA. Generated EMF of phase A, which is always taken as 1 angle 0, minus IA1. IA1 and IA0 are the same, that is minus J 1.4286 into Z1. So Z1 is given as J 0.25. J 0.25. So solve this. You will get the value of VA1 as 0.6429 per unit. So next is VA2. Okay. And VA2 will be equal to minus IA2 Z2, which is equal to minus IA2 is again minus J 1.4286 into Z2 is J 0.35. So answer will be equal to minus 0.5 per unit. Okay. So we got the sequence components of phase A voltage VA. VA0, VA1 and VA2. Now we can write VA, VB and VC. So we know how to express phase voltages in terms of symmetrical components. We have the equation VA, VB, VC equal to the transformation matrix 1, 1, 1, 1 A square A, 1 A square into the symmetrical components of phase A voltage VA0, VA1 and VA2. So from this we can write VA is equal to VA0 plus VA1 plus VA2, which is minus 0.1429 plus 0.6429 plus minus 0.5 per unit. So answer will be 0. Okay. So if you add these three values, it will be a value near to 0. It may not be exactly 0 if you add up these three values. But actually it is not necessary to add these values in order to get the value of VA, because we are assuming that a short circuit is occurring on phase A. Phase A is directly connected to ground. Short circuit on phase A means voltage of phase A will be 0. So we need not add up these three voltages. We can directly write it as 0. Okay. Now VB. VB will be equal to VA0 plus A square VA1 plus A into VA2. So VA0 plus A square VA1 plus A into VA2, that is VB, which is equal to VA0 is 0 minus 0.1429 plus A square into VA1. A square is 1 angle 240 into VA1 is A square into VA1. VA1 is 0.6429 plus A into VA2, that is 1 angle 120 into VA2 is minus 0.5. Okay, solve this. We'll get the value of VB as minus 0.2144 minus J 0.9898 minus J 0.9898 per unit. Okay. Now let us calculate VC. VC will be equal to 1 into VA0 plus A into VA1 plus A square into VA2. VC is equal to VA0 plus A into VA1 plus A square into VA2, which is equal to VA0 is minus 0.1429 plus 1 angle 120. A is 1 angle 120 into VA1, that is 0.6429 plus A square into, that is 1 angle 240 degree into VA2, that is minus 0.5. Okay, solve this. We'll get the value of VC as minus 0.2144 plus J 0.9898 per unit. So we have calculated all the phase voltages VA, VB and VC. So we got VA, VB and VC. Now we can calculate the 3 line voltages VAB, VBC and VCA. So VAB will be equal to VA minus VB. We have VA and VB. Subtract those two voltages. The answer will be 0.2144. 0.2144 plus J 0.9898. Okay. And in polar form, VAB will be 1.012 angle 77.77 degree. Now VBC, it is equal to VBC will be equal to VB minus VC, which is equal to, we have VB and VC, subtract VB and VC, then we will get VBC is equal to minus J 1.9796 per unit. 1.9796 per unit. Okay. Then calculate VCA, which is equal to VC minus VA, and value of VCA will be minus 0.2144 plus J 0.9898. And in per unit, this will be equal to 1.012 angle 102.22 degree. And here this can be represented as 1.9796 angle minus 90 degree. So we got all the line voltages. So question was to calculate the subtransient currents in the generator as well as the line to line voltages. So we have calculated the subtransient currents as well as the line to line voltage. And always while solving the symmetrical fault analysis problems, try to express those quantities which are asked in the question in their actual value, as their actual value. So always try to write the actual value of the quantities which are being asked in the question. So we had to calculate the subtransient currents in the generator, and that was IA, and actual value of IA, which is equal to the fault current, that we have already calculated. And the next parameter which is asked in the question is the line to line voltages. So we have calculated the per unit values of the line to line voltages. So these are the per unit values. Now let us express this in their actual value also. Also write the actual values of the line voltages as they are actually being asked in the question. So line voltage actual value will be per unit value into base value. So VAB actual, which is equal to per unit value into base value of voltage. So per unit value of VAB is 1.012 angle 77.77 degree per unit into base value. So here line value of base voltage is 13.2. The generator is having a voltage 13.2 kV, but here we have to multiply this voltage VAB by the phase value of base voltage, that is 13.2 divided by root 3, and answer VAB will be equal to 7.71 kV, 7.71 angle 77.77 degree kV. So why we are multiplying this line voltage with the phase value of base voltage? Because actually even if VAB denotes the line voltage, we have calculated VAB by subtracting two phase voltages, VA and VB. So numerically it is the difference between two phase voltages. So we have to multiply that by the phase value of base voltage, that is 13.2 divided by root 3. Now similarly VBC actual is equal to its per unit value, that is 1.9796 angle minus 90 into 13.2 divided by root 3, and this will be equal to 15.08 angle minus 90 degree, and VCA actual will be equal to 1.012 angle 102.22 into 13.2 by root 3, and this will be equal to 7.71 angle 102.22 kV. So this is also kV. So this is how unsymmetrical fault analysis is done.